I'm happy to let you know that today's first plenary talk by Professor Paul Linden is also the William Mong Distinguished Lecturer in Engineering at the University of Hong Kong. The University of Hong Kong, this William Mong Distinguished Lecturer at the Faculty of Engineering at Hong Kong U is supported by William M.W. Mong Engineering Research Fund. Thank you.
Testing. Very good morning to everyone. My name is Alvin Nai from City University of Hong Kong. Sitting beside me is Professor Tham Kok Wai from National University of Singapore. This morning, we are very honored to have two distinguished plenary sessions, both related to the environmental fluid flow and sustainability. The first prominent speaker is Professor Paul Linden. Professor Paul Linden, FRS, currently G.I. Taylor Professor of Fluid Mechanics at Cambridge. He was the Basker Professor of Environmental Science and Engineering at University of California, San Diego. Professor Linden was previously in DAMTP for many years, starting as a research student and ending as reader in geophysics fluid dynamics before leaving for San Diego in 1998. He is a fellow of Royal Society, elected in year 2007, and is internationally known for respect for his laboratory experiments and theoretical analysis of fluid flow relevant oceanography, meteorology, and environmental and industrial problems. In San Diego, he has been chair of the Department of Mechanical and Aerospace Engineering. Professor Linden is a leading figure in environment and sustainability research, and he is currently director of UCSD Sustainability Solution Institute. His appointment not only strengthens this area in DAMTP, but connects to important activities elsewhere in the university, including the Center of Sustainable Development in the Department of Engineering. Without further ado, let's welcome Professor Paul Linden.
Well, thank you very much, and good morning. So I'm going to talk about the fluid mechanics of sustainable buildings. If I can make this move. I'll say down. Okay, thank you. All right, so why are we concerned about sustainability and buildings? And the picture on the left shows the carbon emissions in metric tons of carbon for 3 sectors of industry, and you can see that buildings contribute significantly and are the fastest growing sector in this area. And this development is highlighted by where we are at the moment. The picture on the right is Hong Kong, which has seen enormous growth, has many other cities around the world, and these buildings use lots of energy. Nevertheless, there's a general feeling that many of the modern buildings are relatively uncomfortable, and so there's a question of designing buildings that are also comfortable as well as low in energy usage. So historically, the first air-conditioned building was designed by Frank Lloyd Wright and built in Upper New York State at the beginning of the 20th century. And what's remarkable about this building, I'm afraid it no longer exists, it was demolished, is that it looks nothing like the modern buildings that I showed on the last slide. It is what you would imagine a much more traditional building looks like, with thick walls and small amounts of glazing. And this is because when air conditioning was first introduced, it was just introduced into a traditional building design. And we've now changed that design into these glass structures that receive solar radiation and require significant amounts of cooling. The issue really is clear that cooling is the major contributor to this process in terms of ventilation. If you take a typical one-person office and imagine that this person is giving off around 100 watts of heat and requires around 10 liters per second of air for comfortable carbon dioxide levels, then that implies just a temperature difference of 10 degrees between the outside, 10 degrees C, and the interior, 20 degrees C, and that's a very comfortable temperature difference. And so for heating, you don't need to do very much in order to provide comfort. But on the other hand, if you go to the cooling situation, then it's quite the reverse. In this case, the temperature difference, if it's 10 degrees, means that if it's 25 outside, it's 35 inside, and that, of course, is very difficult to tolerate. So you need to provide additional ventilation in the cooling season, and this is why we air condition buildings with huge energy considerations. So it really is the cooling that's the challenge from a fluid mechanical point of view, which is my perspective on this, the airflow question and how you remove the heat. This is the major challenge, and what we're going to do is to look at various mechanisms for developing ventilation flows that require low amounts of energy. So what's the practical challenge? The practical challenge is that we want to provide guidance for designers. We want to know what is the most energy efficient design? How can comfortable conditions be achieved in a building subject to natural variability and external weather? And how can occupants have control over this environment? And in order to provide this guidance, we need to be able to model these buildings to provide accurate calculations for energy consumption and for the internal conditions. And these calculations need to be run over long periods of time. For example, this shows 2 years' worth of weather data in San Diego, where I used to live, and you can see it's a very pleasant climate. The temperature on the left is in degrees Fahrenheit, so it's never very hot and never very cold. But nevertheless, you have to run a building against this kind of weather information. So the models have to be fast and robust. And the buildings are complicated. Here is an example of a new building. It's the headquarters for the New York Times, opened in 2009. The middle picture shows the wonderful structure designed by the architect Renzo Piano, and the interior is shown on the left, open plan floors. And just to give you an idea of the complexity, this building is air-conditioned. It uses underfloor air conditioning, and the floor plate is shown on the right-hand picture. So this is an extremely complicated system, and one of the major challenges is how to predict the performance of such a building. And I'll come back to this issue towards the end of my talk. So as I said, this is the practical challenge, and what we need is simple and robust models to calculate building energy consumption and the internal temperatures and ventilation rates. Okay, so I'm going to talk, to start with, about stack-driven ventilation, and that is ventilation driven by temperature differences, in this case between the interior and the exterior of a building. And there are two modes at which you can operate. So if you imagine the building on the left, there's a certain amount of heat imposed into this building, internal gains or through the fabric, and you want to remove that heat. You can either stratify it, as shown in the building on the left, so the hot air accumulates at some location near the top of the space, or you can mix it so that the temperature is evenly distributed throughout the space. The difference, of course, is that on the left, the temperature leaving the space is on the top right, is the maximum compared to the building on the right. And so you can get rid of the same amount of heat with a much lower flow rate if you stratify compared with if you mix the system. So there's a lot of emphasis on providing stratification and then trying to understand the implications of that for things like comfort, indoor air quality, and so forth. And just to give you an example of that, I don't know if I can make this work without touching it. How do we do that? There we go. Okay. Well, one works and one doesn't. Sorry, I'll just go back a bit. Try that again. No, okay. Okay, so the one on the left is, this is displacement ventilation. So cool air is entering at the lower part of the building, and warm air is leaving at the upper part, as you can see. And the system is stratified, so the warm air is near the ceiling, and the cool air is lower down. So this is just displacement ventilation. This is the stratified case. And on the right-hand side now, we've changed the configuration. So the opening that was at the bottom on the left-hand picture is now at the top. And what you can see is that that produces mixing throughout the space. And the temperature, as you can tell by the relatively uniform color, is essentially uniform throughout the whole space. So by a simple rearrangement of where the openings are, it's possible to develop these two forms of ventilation, just driven by the temperature differences between inside and outside the building. And I can tell you, although because if I'd run these movies together, you would see that the one on the right is much less efficient than the one on the left. It takes about 5 times as long to remove the heat from the building on the right to the one on the left. So what's the fluid mechanics challenge? The fluid mechanics challenge, I think, in buildings is really a very unique one. We have engineered flows, such as the flow on the left around an aerofoil. The flow, in this case, is very much determined by the geometry of this configuration. So the shape of the aerofoil, the angle of attack, the speed of the aerofoil through the fluid tells you everything you need to know about this system. You don't care very much about the properties of the air itself. On the other hand, for a natural flow, like this cyclone that I show here, this is really irrespective of the boundaries of the system. It just depends on its internal dynamics, in this case, the release of latent heat and the rotation of the Earth. In a building, you have both of these components together. You have the fact that the building shape dominates what goes on, where the openings are, as I just showed you, makes a big influence on the internal flow, but also the internal dynamics matter hugely. What's going on inside this auditorium depends on the natural dynamics, the temperature variations in this room, and so forth. So it's a very complicated problem involving complicated internal dynamics and complicated geometry, and that's the real challenge. And one way to tackle this is to do laboratory experiments. And we've been very successful, I think, over the years in modeling flows in the laboratory. And I just show you 2 examples where you can extrapolate from small-scale laboratory experiments to large-scale physical flows. So the pictures on the left are gravity currents. These are flows driven by density variations. And the lower one is in the laboratory. It's about 10 centimeters in size. And the one in the atmosphere, as you can see by the height of the buildings, is considerably larger. And we're able to reproduce the same physics in the laboratory as in nature. The same is true for plumes. This is an oil fire that took place in the UK. And we can model this in very small tanks in the laboratory. The predictions of the graph on the lower right are over 5 orders of magnitude in scale. We think this is the second largest extrapolation in physics. Okay. And this all comes back, of course, to Osborne Reynolds, who did his famous experiments in a pipe, transition to turbulence, and pointed out that the dynamics that matter, the balance between inertia and friction, is determined by this dimensionless number, the Reynolds number. And you can see that in this system, the scale of the system, L, is dominant. So when you reduce from a full-scale problem to a laboratory experiment, what you do is you make L smaller, and this reduces the Reynolds number and increases the effects of friction. And so the challenge in these kinds of experimental approaches is how do you make sure that those frictional effects don't dominate when you come to small flows. So this is the kind of approach that one takes. This is a typical office on the left, and on the right is a laboratory model of such an office, a tank which is then placed in this tank on the left-hand side. We do experiments where we reduce the scale by factors of 10 or 20 or so. And so the Reynolds number is reduced by significant fractions. And so the way to alleviate this is to use water, because water is less viscous than air. So we do experiments in water, and the ones I showed you, the movies I showed you before, were in water. We provide buoyancy with salt rather than temperature, because this gives us faster driving. This means that we can recover a factor of 30 or so of this factor of 100. And so our Reynolds numbers are comparable at small scale and large scale. So the models give faithful reproductions of what goes on. So we can analyze this flow for a single plume, for example. So now we have displacement ventilation. The flow you can see leaving, the warm air is leaving at the top right of the picture, and cool air is entering at the lower part. And what you see in this configuration is a single plume from a heat source, and it sets up a stratification in this space which consists of 2 layers separated by a sharp interface, this interface along here. So there's a warm upper layer and a cool lower layer. And the design here is to make sure that you occupy this part and this part is above your head. So I'm going to just run through the analysis of this flow. Oops. So, well, this is a, oops, sorry. Can't seem to get this movie to play, but this is a plume rising from a person. All of you are giving off plumes as you sit there. Each of you gives off about 80 watts or something like that. And from that, we can calculate the flow above in this situation, and we can relate in particular the velocity in this plume to the temperature difference, and therefore the amount of air that's carried upwards, this volume flux, in terms of the temperature difference and the height above the person. And so now we can analyze the experiment that I just showed you. So air enters at low level. It gets entrained into this turbulent plume, maybe from a person or from a computer, and then leaves again at the top of this space. And consequently, the amount flowing in here, Q, must be the same as the leaves at the top. And so that's the flow rate across this plume here, which we have a formula for in terms of the height of this interface and the strength of the plume. Similarly, the heat balance tells us that the heat flux in here must be the same as the heat flux leaving there, which tells us what the temperature of this upper layer is. And so we can do the analysis for this system. If we remove the plume, we go back to the movie that I showed you before, where this hot layer just drains, and you can calculate the rate at which this hot layer drains by calculating the pressure drop across this opening and the pressure drop across this opening. I won't go through the mathematics, but you can calculate the flow rate in terms of an area, the temperature difference between these 2 layers, this delta T, and the height of this upper red layer here, H minus H. And the point about this area is that it's a composite of the lower area AL and the upper area AU. And I'll show you that that's really important. So we go back, this is the same formula as before. Now let's suppose, and I'll show you this is typical in a building, that the area of the openings at the top of the building are small in comparison to the area of the openings at the lower part of the building. Then if we take this formula for this combination of openable areas, A star, and make AU, this quantity, small, so we neglect it relative to this, then of course this square root just cancels the square and these cancel out, and so this is approximately AU. Okay? So the flow is controlled through the smaller opening, and that means that you have local control on the system. Okay? And the consequences of that are, in a building like my department, is that we allow the warm air to leave the department through these thermal chimneys, which have small openable areas. So the whole building, which has lots of openable area around and these windows, is controlled by the flow through this small openable area. The other feature of this system is that you can calculate the height of the warm layer, and it has a formula like this, where H is the height of the cool lower layer and big H is the height of the room. And you can see that when these become close to 1, when the cool layer gets close to the ceiling, this denominator becomes small, and so you need lots of openable area. And the way you get around this problem is to make an artificially tall space by adding chimneys to make this capital H large. So both of these, this building just embodies both of those very simple principles based on that analysis. We can also include the effects of wind on a system like this. So this is the case of an opposing wind, where the wind blows through the building in the opposite direction to the ventilation flow. When the wind blows weakly, we just reduce the effectiveness of the ventilation, so we make it warmer and bring this interface down. If we blow very hard, we can actually force the flow to go right back in the opposite direction and become a mixing system. So it changes the ventilation mode completely. Okay, so that's all to do with temperatures and how buildings ventilate. Of course, when you're all sitting there, you're wondering how comfortable you are. What I show here is a study carried out in Cambridge on overall comfort compared to the CO2 emissions of various buildings. So down here are naturally ventilated buildings with relatively low carbon emissions, and up here are fully air-conditioned buildings with high carbon emissions. And what you can see on this comfort scale from unsatisfactory to satisfactory is there's really no difference. People are equally comfortable or uncomfortable depending on irrespective of the building type. So the question is, how can we move down this scale in terms of energy consumption while maintaining comfort? And how do we know about this? Well, we know about this because of pioneering work carried out by Ed Ahrens and his group at CBE, where they've done some extremely wonderful work looking at subjects on sensation to temperature. And I think some of the interesting work here is they show, for example, that there's a real asymmetry between hot and cold. Your body temperature is 37 degrees, and so you feel much less tolerance to temperatures that are high and close to 37 degrees than you do for temperatures that are much colder than you are. And so this asymmetry, again, means that cooling is a major problem in this system. And what they show is that when you're in stable conditions, you tend to be uncomfortable if 2 of your body parts are uncomfortable. But in transient conditions, even if you're uncomfortable, you can become comfortable if 2 body parts are made comfortable, even if the rest of your body is not. And I always like the idea of being cold in the winter and being really cold, and you come in and stand by the fire and put your hands in front of the fire, and if your hands are warm, you feel fine, even if you're still cold. So transient effects matter a lot. And so again, it's a question of how do you design spaces so that these transient processes can be incorporated. So we then look at possibilities of chilled ceilings and beams, natural variability of solar radiation, natural variability of wind flow externally, and local control. The idea of producing personalized fans, air movement, becoming more and more the vogue in terms of providing comfort in these buildings. Well, I thought I'll show you some examples then of some, one example of a naturally ventilated building. This is the San Francisco Federal Office Building, opened in 2008, I think, or 2007. It's a naturally wind-driven ventilation system with this very interesting facade. Wind blows from one side of the building to the other through openings. Some of these openings are controlled by the building management system. Some of them are controlled by the individuals. Has a lot of thermal mass. You can see all this concrete in this region here to absorb heat during the day and re-emit it in the night. One of the interesting features in a building like this is that the behavior of the occupants matters enormously. So this graph shows the temperature variation over 3 hot days in San Francisco. What you can see, comparing the red graph and the green graph, is that if the occupants are well informed, the temperatures are ameliorated inside. If the occupants are poorly informed, the temperatures inside are almost the same as outside and very high, above 30 degrees. So occupant behavior in these buildings now becomes an important ingredient in the way the buildings operate and perform. So that's naturally ventilated buildings. I wanted to spend a minute or two talking about underfloor air distribution. In this case, this is an air-conditioned system. It's the one that was employed on the New York Times headquarters building I showed you earlier. And in this case, cool air is brought in through an underfloor plenum, through these vents in the floor, and then discharged at high level through vents in the ceiling. And in contrast to typical air conditioning buildings where the cool air is introduced at the ceiling. So it captures some of the features of the displacement ventilation system that we looked at in the naturally ventilated case. See if I can get these movies to work. I really don't have a map. Oh, maybe my mouse will do it. How do I do that? Ah, there we go. Good. That's what I wanted to do. Okay. So what you see on the right is on the left is a test room with smoke coming through one of these underfloor vents, and on the right-hand side a laboratory model of exactly the same system. And you can see that the smoke, as it rises through here, accumulates in the lower layer. There's a warm layer stratified near the ceiling. We have the same variation here on the right-hand side with the smoke, with the dye indicating a warm layer here. So again, we're able to produce in the lab the same features as at full scale and make models of this flow. And this enables us to do things like calculate how you operate the system for demand response. So we're able to make adjustments to the system to reduce demand at peak times, depending on how you operate the system from the models that we've developed. Okay, so this is all kind of modern buildings. I want to spend the last part of my talk talking about what we do with existing buildings. Most of our building stock, of course, is in existence. We only replace 10 or 20% in any one year at the most. And so how do we go about retrofitting existing buildings? The simplest thing to do for a sealed air-conditioned building, of course, is to open some windows. what I'm going to do is to look at the possibility of what you can gain from just opening windows. This, of course, allows wind-driven ventilation, and there are various modes of this, which I'll show you in a second. And I'm going to concentrate on single-sided ventilation, that is where the windows are open just on one side of the facade. So here is a typical building, and with the possibility of opening windows on this side, and in this courtyard, you can generate cross-ventilation, or in this case here, where you open two windows on one side, you just have single-sided ventilation. We're going to just concentrate on this case, partly because it's, I think, more interesting. Fluid mechanics is a more interesting problem. But it's also the one that's most likely to be achieved in many circumstances. So we're going to look at the possibility of two openings in a single space, and we'll look at the effect of the wind blowing on this building at various orientations and the effects of changing the location of these two openings. So this was done in the wind tunnel by a company in Colorado, CPP Wind Engineering, by David Banks. I have this model here of a building with various openings, and this is mounted in a wind tunnel. And from this, we're able to measure the flow rate, ventilation flow rates in the system and the pressure distribution around the building. So what this shows here is the wind angle. So this is when the openings are in the lee of the building. This is where on the side. This is when they're on the front face of the building, facing the wind. What is shown here is the ventilation flow rate for two sets of openings, the red ones where they're widely separated, and the yellow ones where they're close together. So first of all, you can see that the more widely separated excuse me, openings tend to give a higher flow rate, and they both have a similar variation with wind angle. So they increase when the wind moves away from the lee, has a minimum when it's roughly going parallel to the side of the building, and then increases again as you come round to the front of the building. And the same picture exists in the pressure variations measured at the two windows. So there's a clear indication here that the pressure differences across the two openings are really what's driving this flow, which is not particularly a surprise. So let's see if I can get this to work. So here's some flow visualization of the case when the wind is coming from the left, and these two openings here are in the lee of the building. So now you can see actually that although we were looking at a ventilation flow here, the mean pressure difference is relatively low, but actually there's a significant flow here associated with the vortex shedding from the edges of the building. And this flow alternates because the vortices shed around this building. So first of all, it's outflow from here, followed by a period of inflow now, and then followed by a period of outflow, and so forth, back and forth. So this pumping flow is a very effective mechanism of generating wind-driven ventilation, even in the lee of the building. So, as a result of this, we're able to build a model which takes account of the pressure variations, both the mean pressure variation and those unsteady pressure variations that I was showing you in that movie. What these pictures show you are simply the comparisons of the data in red with the model that we've generated for these various configurations. So for a range of different separations and orientations of the building, we're able to predict with a mean error of about 25% the ventilation in this wind-driven system. So that brings me to my conclusions. So I want to say that I believe that significant energy savings are achievable through the study of fluid mechanics of buildings, architectural fluid mechanics, that there's an increasing use of unconventional natural ventilation, using natural ventilation in ways that use the thermal mass, for example, that use personal comfort devices to provide air movement, and a range of other possibilities. And there are many future challenges. I still think the problem of optimizing for comfort is a major challenge in this whole area. There are interesting problems associated with new mixed mode and hybrid buildings where you combine natural ventilation and other methods for cooling. Recent work that we're doing at the moment is looking at replacing thermal mass with phase change materials and other such devices to improve ventilation efficiency. And with that, I thank you for your attention.
Thank you, Professor Linden, for giving us such an interesting presentation on how fluid mechanics apply to solve the indoor airflow. And I think most of you found the movie very interesting. Let us give Professor Paul Linden another big hand.